Hi, this is Kevin. Welcome to my lecture on uh, Chapter 7 of the Zelle 3rd edition Python programming book. And Chapter 7 is about decision structures. Uh, as usual, I'm going to leave you to read the objectives on your own. Okay, so simple decision. So far, we've we've been viewing programs as sequences of instructions that are followed one after the other. In fact, I talked about that in my lecture for Chapter 6. While this is a fundamental programming concept, it's not sufficient in itself to solve every problem. We need to be able to alter the sequential flow of a program to suit a particular situation. And when you really think about this, you realize that some of the value of computer programs is helping us to make decisions and to choose. We want the behavior of the program to be customized to the present circumstances. And so we need this kind of decision-oriented logic in our program. And in Chapter 7, we're going to get the constructs to make that happen. So control structures allow us to alter the sequential flow of a program. In this chapter, we're going to learn about decision structures. They're part of control structures, which are statements that allow a program to execute different sequences of instructions for different cases, allowing the program to choose an appropriate course of action. So what we're going to do is we're going to take a program that we created in Chapter 2, which converted Celsius temperature values to Fahrenheit values. And we're going to make it more complex. Okay? So if you wanted to see that program in detail, you go back to Chapter 2. So how do we want this new program to be different from the one we did in Chapter 2? Well, let's say we want to modify the program to print a warning when the weather is extreme. So any temperature over 90 degrees Fahrenheit or lower than 30 degrees Fahrenheit will cause a hot or cold weather warning, respectively. Okay, so here's some pseudocode. Input the temperature in degrees Celsius. Call it Celsius. That's what he's suggesting for a variable name. Calculate a Fahrenheit as 9/5 times Celsius plus 32. And even if we were doing just regular old algebra, I would expect him to have grouped 9/5 times at Celsius with parens. Output Fahrenheit. Okay, so we're going to print the Fahrenheit temperature, but then we're going to go further and we're going to say if the Fahrenheit temperature is greater than 90, print a heat warning. If the Fahrenheit temperature, I think what he meant to say here was less than 30, we're going to print a cold warning. This new algorithm has two decisions at the end. The indentation indicates that a step should be performed only if the condition listed in the previous line is true. And that's kind of how the syntax of Python works, which is why the pseudocode for Python takes on that form. Now, here's the same logic expressed as a programmer flowchart. Now, I've mentioned a couple of times in my lectures that programmer flowcharts are interesting, and I think they're a good teaching tool. But we don't typically teach students to create them because of the fact that you're able to diagram a lot of program logic that we wouldn't want you to code. And so we typically would like you to use pseudocode as a kind of sketch tool while you're working on your design of your program, and not programmer flowcharts, whose time is really come and gone. But they're still nice to illustrate a point or two. So we're going to begin by inputting the Celsius temperature. We're going to calculate the Fahrenheit. So we're going to print the Fahrenheit. And then we come to a diamond, which is a decision. Okay. So we say Fahrenheit greater than 90. So if that's a yes, that's true, then we want to print a heat warning. Okay. And if that's false, it's a no, then we don't want to do anything. And you can see how we come back and we join the main flow of the logic right there. So then we go into a completely separate if test. So we ask if the Fahrenheit is less than 30, and if yes, then we print a cold warning. Otherwise, we don't do anything at all. Okay, and what I want to emphasize here, and we can see it from the programmer flowchart, is that these are two simple ifs. One if, two ifs. And if we back up and we look at the pseudocode, we see the same thing. Two simple ifs. Okay? So when we get to the Python code, it's not going to surprise us. So the program is called convert2, and I'm going to bring that over in PyCharm so we can see it. And it's got the normal problems. It's got the wrong kind of comments. It's maybe not formatted the right way. It's got more comments than we need in the body, etc. So I've refactored it to convert to refactored. Okay. So now we begin with a docstring. So what I did is I took the two comments that we had here, and the general one that summarizes the program, that comes first. If we have more details, then we skip line 2 and then we start the details on line 3. So that's how we did that. Let's see, this first line, I've just updated the quote marks to make them singles rather than doubles. On line 10, we have grouped 9/5 times Celsius with parens because that's a better practice. When we print, even though F strings are not covered in the textbooks, they really are a current best practice. So I've converted the line that he had here, line 11, to use an F string. Okay. And then we check if Fahrenheit is greater than 90, and if it is, we print out a warning, and then we check if it's less than 30, and we print out a warning. And I just want to print out one thing. If the Fahrenheit is greater than 90, right, it's never going to be true that it's also less than 30. Okay, so this is a pretty simplistic approach and maybe a little bit inefficient because if we pass test 1, we already know we're going to fail test 2. And yet we haven't taken that into account when we write the code. And that's because we're just learning about simple ifs. Okay, and this is how you do this with a simple if. Okay. There's not a lot of alternatives to this shown in the text. And so there's not a lot of discussion of alternative approaches to this temperature related problem here. But that's something I do cover in my supplemental material. So um, keep an eye out for that when you get there. Okay. And so let's give this a test first. Okay, so let's run it. And what's the Celsius temperature? Um, in Europe right now, it's very, very hot. It's gotten up to 40 degrees. So 40 is 104. So that's pretty cold. Okay, and then let's just run that again. And let's say we've got it's 0 Celsius. Okay, and it says the temperature is 32 Fahrenheit. We still didn't get a warning. So I guess we're going to have to say it's negative 5 Celsius. And then there it got 23 degrees Fahrenheit and we got a cold warning. Okay, so that's the refactor version of convert to. All right. So the form of a simple if is if condition, okay, and then we have a colon, and then indented, one indent is the body, okay, which can be one or more statements. In the code that we just saw, it was only one, but it can be a series of them. The semantics of if should be clear. First, the condition in the heading is evaluated. If the condition is true, the sequence of statements in the body is executed, and then control passes to the next statement in the program. If the condition is false, the statement in the body are skipped, and control passes to the next statement in the program. Okay, and again, a programmer flowchart here, not because we want you to learn how to draw them, but because it is worthwhile to know how to read them. So there's a test, okay, and there's a condition. So we're essentially asking if it's true. So yes, if it's true, then we do the statement or statements in the body. If no, well, then we don't do anything. And in both cases, we join up and then we drop through and we go on to the next statement in the program. The body of the if either executes or not depending on the condition. In any case, control then passes to the next statement after the if. This is a simple or a one-way decision. Okay, so what does a condition look like? You know, we've said, what do we said? We said if condition, and back here we were saying if condition. So what do we mean by condition, right? Well, it's usually made up of three parts. And what we see here is kind of a syntax diagram for that. So we have an expression. We have a relational operator. That's what we mean by RELOP. And we have another expression. Okay. So what are the relational operators? Well, we've seen some of them already. We've seen we've seen greater than, we've seen less than. So this is an interesting slide because it shows you the Python code. It shows you how it would be written in math notation, for instance, in a textbook or maybe on some slides. And then it has an English version of what the meaning is. So The less than sign is less than. The combination of the less followed by the equal as a group is less than or equal to. If equal followed by equal, 2 equals is equal to, okay? Remember that 1 equal is assignment, okay? So if we want to do a comparison, the relational operator is equal equal. A combination of a greater than and an equal will be greater than or equal to. Just the greater than is greater than. And not equal is the combination of the exclamation, sometimes called the bang symbol, and the equal, not equal. Okay. And now, why do we call that the bang? All I know is that in silent movies, where there was no sound, if somebody shot a gun, you'd see a little flag come out of it, and there'd be an exclamation mark. And I think that's how we came up with the name Bang. I don't know. But programmers often call the exclamation Bang. Okay. Notice the use of the double equals for equality. Since Python uses the single equal to indicate assignment, a different symbol is required for the concept of equality. Well, that's not absolutely true. We know that Python has other overloaded operators, right? It just made it easier to write the Python interpreter that we use equal equal for equality and single equal for assignment. And once you get used to it, it makes for better reading of code. But the fact is, it could have been different. They just decided not to do it. A common mistake is using the single equal when you're trying to make comparisons. And unfortunately, that's valid Python that means something different. Okay, so this makes it a common error. Conditions may compare either numbers or strings. Okay. They could even compare other types. So you can compare any type to any other type with an equal equal, but certainly numbers and strings are done most commonly. When comparing strings, the ordering is lexicographic, meaning that the strings are sorted based on the underlying Unicode. Because of this, all the uppercase Latin letters come before the lowercase. So a capital B, all lowercase b's, comes before lowercase a's. Now this is inconvenient, but that's the way it works. You get used to it. The trick is, if you're going to try to sort things, you want to sort them when they're when they've been made equal in their case presentation. Then they're going to sort just fine. Conditions are based on Boolean expressions, named after the English mathematician George Boole. When a Boolean expression is evaluated, it produces either a value of true, meaning the condition holds, or it produces a false, it does not hold. Some computer languages use a 1 and a 0 to represent true or false. Python does not. Okay. In Python, the type of variable, the value type that holds true and false is a bool, short for Boolean, and its literal values are true, capital T-R-U-E, no quotes around it, and false, capital F-A-L-S-E, no quotes around that either. So here we are at the console, the REPL. So we put in the expression or the comparison 3 less than 4. It evaluates to true. and then we put in 3 times 4 less than 3 plus 4, that evaluates the false. I would have wanted to seen parens around this. Again, I am a stickler for readable code. We ask if the string hello is equal to the string hello. It says true, it is. We ask if the string hello with a capital H is less than string hello with a lowercase h. It says true because all the capitals sort before all of the lowercase. It seems odd, but that's the way that the Unicode encoding scheme is ordered. Okay, so that's it for the comparisons and sort order and stuff. We're on to a new issue, okay? And it has to do with potential use for the simple if construct, okay? So in the programs that we've written so far, these have all been programs that we're going to run by themselves, okay? None of them has been a library module that includes, for instance, a function, so that we want to import the module and we want to import the module, import the function from the module, and then we want to call it, okay? It turns out that if you want that kind of architecture to work the right way, you need to change the call to main that happens at the bottom of the program. So that's what we're talking about now. So there's several ways of running Python programs. Some modules are designed to be run directly. These are referred to as programs or scripts. That's what we've been writing all along. Others are made to be imported and used by other programs. These are referred to as libraries. And so far, we haven't created any of those yet. We will soon, okay? But we have imported things from library modules, for instance, the math module. Sometimes we want to create a hybrid that can be used as both a standalone program and as a library. And we'll see how to do that, okay? When we want to start a program once it's loaded, we include the line main, paren, with an invocation to the main function at the bottom of the code, okay? Since Python evaluates the lines of the program during the import process, our current programs also run when they are imported into an interactive Python session or into another Python program. Well, that's a side effect, and not really a problem because we haven't intended for the programs that we've created so far to act as some kind of a library module, okay? But if we did import them, they would run, and that's not typically what you want when you're importing code. Generally, when we import a module, we don't want it to execute, okay? We only want code to execute from the module when we call that code, okay? And if you remember back to when we imported functions from math, for instance, when we imported the math module, it didn't run. Okay, and then when we called the function that we wanted to call, well, that function ran. So what we're trying to do is say if we want to make a .py file that can be used as a library module, how do we have to do things a little differently than we've been doing so far? And then what happens is, down at the very bottom of our program, we can't just have a simple call to main. We need to test a condition, and if that condition is true, we'll call main. Well, what's the condition that we need? Well, we want to call main if we're running this program all by itself. Okay? If we're running this program all by itself, then we want to run it. Okay? Okay, so we need to find out what the text of the condition is. Okay? Whenever a module is imported, Python creates a special variable in the module called dunder name. Whenever anything is preceded and usually suffixed by double underscores, we say that it's dunder, double underscore dundered. So dunder name is the name of a variable that is set to the name of the imported module. So if we, down at the REPL, import math and then we ask for math.dunder name, we can see that the dunder name of math is math. Okay, so we're going to rely upon this when we craft the code that is going to keep this thing from running when we don't want it. When imported, the dunder name variable inside the math module is assigned the string math. When Python code is run directly and not imported, the value of dunder name is main. Okay. So to recap, if a module is imported, the code in the module will see a variable called dunder name, whose value is the name of the module. When a file is run directly, the code will see the value dunder main. We can change the final lines of our programs too, and this becomes, this is the code that you replace the simple call to main with. Okay, if dunder name equals dunder main, then run main. Okay, now he goes a little bit farther and he says, virtually every Python module ends this way. Now, if you look at the code in the remaining chapters of the Zelle book, he uses this a lot. He uses this a lot. By contrast, you'll see that I'll be teaching you to only use this more complex version if you are creating a library module. Okay. Now, one of the things he points out is we have some code that's never going to be used as a library module. That's probably most of the programs that we're going to write. And then we have some code that just is a library module. It's just, for instance, it's a bunch of functions, but it has no real main. It's just a bunch of things to be shared. Okay. Well, that's always going to have that would always have something like this to keep the main from running. In fact, if it doesn't have a main, we probably don't even have to call main. This kind of code is for people who want to have it both ways. An American expression for that is have your cake and eat it too. So if you want a program that can run all by itself, or it can be imported into another program and you can call functions from it, then you want to put this at the bottom instead of just the call to main. Okay, and that's what I'm going to do. It's only when we have the use case that we are going to import this that we'll put the more complex version at the bottom of the code. Now we come to two-way decisions, and I want to point out that the author gets into a series of programs that use quadratic equations. And he'd used them in another chapter, perhaps chapter 3, and now he's back to using them again. And I don't think that they're a good teaching tool. So I'm not going to talk about these examples a lot. Um, I have not created a refactored version of them. I kind of consider them to be beyond saving. Okay. Uh, I will say that I provide more sample programs in my supplementary material. Okay. But for right now, I'm going to skip over some of these program examples and just concentrate on the slides that talk about the general principles. So this quadratic .pi, I'm going to skip over. And I'm going to go right here to 36, where we get down to general principles. When we say, you know, up until now, we've looked at one-way decisions. Okay. Well, what if we want to have a two-way decision? Well, here's the form of it. We call it an if-else. Okay. So we have if condition, colon, followed by a code block, one or more statements, else, colon, followed by a code block, one or more statements. When Python encounters this two-way if structure, it first evaluates the condition. If the condition is true, the statements under the if are executed. If the condition is false, the statements under the else are executed. In either case, the statements following the if-else are executed after either set of statements is executed. All right, so that's the way two-way ifs work. And now we get back into more quadratics. Okay. And we're just going to go right past them. Okay. And just at the bottom of the slice is, oh, I think we need a three-way decision. Okay. Here on slide 43, we see how we would handle a three-way decision. Okay, well, this is one way to handle a three-way decision, which is called a nested if. So here's what we do. We break it down into two parts. So we distinguish one case from the other two, and then hanging off of the else, we have another if-else, and that's how we distinguish between the remaining two. Okay, it's not the only way to handle a three-way decision, but that's one of the ways to do it. Okay, this is called a nested if. So imagine if we needed to make a five-way decision using nested ifs, that would be a mess. So there's another construct called if-elif, okay, which is more the typical thing that we use for multi-way decisions. And here's the general form here on slide 46. If condition 1, okay, colon, and then we've got the code block for condition 1. Elif condition 2, code block. Elif condition 3, I have a code block. And then we can terminate with an else. That's optional, okay, but generally good form. And so the last thing we have is an else, and that would be the default statement which says, okay, this is a code block which we're going to execute if we don't match any of the conditions on the way down this if-elif. Okay. Now, one thing that is obvious to me, but I want it to be obvious to you, is that the nature of the execution of this is uh, if we test condition 1 and it's true, well, then we just do the case 1 statements and we're done. Okay? If it's false, then we go to the first elif. If that's true, then we do the case 2 statements and we're done. If condition 2 is not true, then we go to the next elif, right? And that continues on through all of the elifs. If you get all the way down to an else and you haven't had a true condition yet, well, then that's where you put your default. So one of the nice things about this if-elif construct is you only test down the chain of elifs if you're not getting matches before it. As soon as you get a match, you do the code block for that match and then you're done. You don't continue testing. It's pretty efficient. This form sets off any number of mutually exclusive code blocks. Python evaluates each condition in turn, looking for the first one that is true. If a true condition is found, the statements indented under that condition are executed, and control passes to the next statement after the entire if, elif, else statement. If none are true, the statements under the else are performed. Right? I just want to point out that while it's good practice, the else is optional. Oh, and so does the author. The else is optional. If there's no else, it's possible no indented block would be executed. And there are times where you just want no behavior. Okay. But I just want to point out that it's always nice to have an else there to make sure that we don't have any silent failures. So now, unfortunately, he dives back into quadratic equations. Once a math major, always a math major, I guess. And we go on and talk about that for a while. And again, I'm not going to humor him in this. If you're a math major and you like this stuff, well, dive in. And if you've got some comments to share with the class, feel free to share them with the class. I don't mean to denigrate your expertise, right? I'm just claiming that perhaps for the general audience, this wasn't the best choice of example for the example code. Okay, so we get to yet another issue called exception handling, and he illustrates it in yet another incarnation of the quadratic program. So we're not going to go through that, but we will talk about this construct. And this is a powerful construct that we're going to be using quite a bit for the rest of the course. And it's called a try except block. Okay. So the try statement has the following form: try colon, and then the body of code, the code block that we're trying to execute. Okay. That's the code block that we think may raise an error. Okay. It's possible for the code itself, just the code that you put into that block, to raise an error, or it's possible for it to call some code that could raise an error. Okay. But either directly or indirectly, we're expecting the code that's executed as part of this code block to perhaps raise an error. And then we have one or more of these except blocks. So we say except the name of the error type and then colon, and then there's a code block to execute if we caught an exception. So the author goes on to say, when Python encounters a try statement, it attempts to execute the statements inside the body of the try. If there's no error, control passes to the next statement after the try, except. If an error occurs while executing the body of the try, Python looks for an except clause with a matching error type. If one is found, the handler code, we call that handler code because it's called handling an exception. So that code block is executed. The original program, so this was the program that he had one of his quadratics. Okay, so the question is, if, okay, if the error type that arises is one that we're expecting, then we get to gracefully handle it. If it's another error, well, then the program's just going to blow up. It's possible, although not really a beginner skill, to catch an exception with this exception handler and then do some work and then rethrow it to raise another exception. Okay, more of an intermediate or advanced Python skill. So instead of crashing, the exception handler prints a message indicating that there are no real roots. Okay, that's in his example program, which I'm kind of on strike with. The try except construct can be used to catch any kind of error and provide a graceful exit. A single try statement can have multiple except clauses, and this happens especially when we're calling code that does complex things, like it opens up a bunch of files or it opens up a connection to a server on the other side of the world. And not just one thing can go wrong, several things can go wrong. And so we might want to recover from each of them in a different way. So we can have more than one except clause as part of the overall block. And now we're back into quadratic equations, and away we go. I'll have more on try except in my supplementary materials. So now we're going to take these constructs that we learned for decisions, and we're going to try to apply them to a common problem. Okay, a common problem that's a little more complex than we've had before. Okay, so suppose that we need an algorithm or recipe or formula to find the largest of three numbers. Okay, so how might we write code to do that? Well, what's he saying? He's saying, please enter three values. Now, he forgot to come back and get rid of eval. Eval is insecure and evil, so we're not, he doesn't really mean to have this eval here. He probably should have said, please enter three integers, or please enter three floats, okay? And then there's some code, which we haven't designed yet, which is going to set the max value to the largest, and then he's going to print the max value. Okay, so the question at hand is, How do we write this code? All right. So he shows a couple of alternatives, and then eventually we settle on a design pattern for finding um, the largest, the smallest, the longest, the shortest. It works generally. Okay. So strategy one, which we're eventually not going to adopt. Um, um, uh, he says this. He has an if. If x1 is greater than or equal to x2 is greater than or equal to x3, max val is x1. Now, the reason I wanted to show this is that it's possible in Python, although not a lot of other languages, to have these multi-step compares. So instead of just comparing two things, you could compare three, which is powerful, or four, or five. Okay, you could do it. And when I first got to Python, I thought this was a bad idea. And what's really happened to me is I've come to like it. If you have a simple comparisons like this, and you're saying, if I have three things and they have this relationship to each other, um, being able to put them all in one statement is a very powerful way to do it. Okay? So definitely feel free to do that. And then, so if this is true, then he wants to choose x1 as the max val. Okay. Whenever you write a decision, there are two crucial questions. When the condition is true, is executing the body of the decision the right action to take? Okay. X1 is at least as large as X2 and X3, so assigning max val to X1 is okay. I would agree. So always pay attention to the borderline values. And it turns out that when we're testing these if-else decision constructs, we talk about this thing called boundary value testing. So the values that are just at the boundary of our different behavior that's being applied, we tend to make our mistakes right at the boundary, right above or right below or right at the decision point. So we try to focus our testing right on those boundary values. And there's a phrase that's commonly used for this, and we use in my course, boundary value testing. Secondly, ask the converse of the first question, namely, are we certain that this condition is true in all cases where x1 is the max? Suppose the values are 5, 2, and 4. Clearly, x1 is the largest, but is x1 greater than equal to x2 greater than equal to x3 hold? We don't really care about the relative ordering of x2 and x3, so we can make two separate tests: x1 greater than equal to x2, and x2 and x1 greater than equal to x3. We can separate the conditions with an and. Okay, so this is probably going to be more general, but you can see this is already getting more complex, and we're only trying to find the biggest of three values. So we eventually are not going to adopt the strategy family that we're talking about here, because it's kind of fiddly and it's not general enough. What would happen if we're trying to find the max of 5 values? Would we need 4 Boolean expressions, each consisting of 4 conditions ANDed together? Yuck. So that's why this kind of family of solutions is not as appealing as maybe we once thought. Okay, so here's another strategy. And again, it's going to turn out we're not going to adopt this one. It turns out to be more fiddly than we want. But we want to take a thing, we want to have something called a decision tree. And decision trees are used in a lot of kind of management science things, optimization problems. They're a great analytical tool. So what you do is a series of decisions, and as you make them, you're kind of going down a tree. So we can avoid the redundant tests of the previous algorithm using a decision tree approach. Suppose we start with x1 greater than or equal to x2. This knocks either x1 or x2 out of contention to be the max. If the condition is true, we need to see which is larger, x1 or x3. So we narrow it down, and then we have a nested if there, or we get a nested if there. Okay, so that solves the problem kind of elegantly, but it's already kind of fiddly, and we've only got 3 values. Again, on the last approach, we kind of surrendered when we imagined that we might want to do this for 5 values, and the same thing here. So here's this expressed as a programmer flowchart. And I've seen programmer flowcharts that are more complex than this, but this kind of makes my head hurt, and I was thinking that it probably would make yours hurt too. This approach makes exactly 2 comparisons regardless of the ordering of the original 3 variables. However, this approach is more complicated than the first. To find the max of 4 values, you'd need if-else's nested 3 levels deep with 8 assignment statements. That's too busy, too fiddly. So we come to strategy 3, and I guarantee you this is the one that we're going to adopt. Okay, so how would you solve the problem? Well, it turns out that there's a general kind of common sense way to solve this. You could probably look at 3 numbers and just know which is the largest. And I talk about this all the time. Humans have a visual intelligence. So we could look at a column of numbers, as long as it's not too big, and we can just scan down and go, there's the largest one right there. Okay. But what if we were given a list of 100 numbers? We still might be able to do it for 100. But let's say we were given 1,000. Well, we couldn't do it visually. Okay. So the approach that we have to take with the program, which hasn't got a visual acuity that humans have, this kind of, probably not visual acuity is the word, but this, kind of visual intelligence, this ability to perceive and reason about things just by looking at the set of values. How would we do this with a computer? I'm going to say that's probably pretty close to the way a human would do it if they had a lot of values. So one strategy is to scan through the list looking for a big number. When one is found, mark it and continue looking. If you find a larger value, mark it, erase the previous mark, and continue looking. Okay, so you're keeping track of the current, what you currently believe is the largest one so far. Okay, and in fact, we can have our program do the same thing. So what do? We pick. So if we've got x1, x2, and x3, we just assume that the first one is the max. And then we say, is the second one greater? If it is, then we move the second one into max. And then we say, is the third one greater? And if it is, then when we remove the third one into max. And so we can just go through in succession. We can assume that the first one is the largest. And this works for the largest, the smallest, the longest, the shortest, the prettiest, the smelliest, whatever you want to do. Okay. You can just assume that the first one is, okay, the whateverest. And then you can just go through them sequentially. That's why this has sequential processing. And if you find one that's larger or smaller or prettier or smellier, well, then uh, uh, you have a new maximum. So this idea can be translated into Python. We could set the max val equal to x1 if x2 is greater than the max val equals x2 if x3 is greater than the max val is equal to x3. Now, if we want this to be a more general solution that'll work with more than 3, well, then we have to adapt it a bit. And we're going to do that with a loop. We prompt the user for a number, we compare it to our current max. If it's larger, we update the max value and we repeat. Okay, so here's an approach. It's called max n. Okay, and I'm going to bring over the PyCharm version. So here's the PyCharm version of max n. And it's got the same kind of frailties that the other programs had. So I've refactored it and created a max n refactored. So the doc string says finds the maximum of a series of numbers. Okay. So then we say how many numbers are there? Okay. And we put that in n. Okay. And then we prompt for the first one, and we just put it into maximum. Now, he had called this max. This is worth a look. You can see that PyCharm doesn't like this variable name max. And if we hover over it, it says it shadows the built-in name max. So there's a built-in function of the same name. And they conflict with each other then in a not a horrible way, but it's not a good practice to name things the same thing as built-in functions. Okay, so I decided to call that maximum. So I refactored that, so that's not called maximum. Okay, so we apparently we're getting floats. Okay, so we say enter a number. Another thing that he had done in the original program is all of a sudden he decides that when he prompts, he wants to use these double greater than signs. Well, all along we've been using a colon. So I just want to point out that we want our users to have regular expectations of what we're going to be doing. Okay, so then, so we take the first one, okay, we assume it's the maximum. Then we do a for loop. We would have said for I in range n, but we've already used one. Okay, so here what we do is we say range n minus 1. And we prompt and we get the next input, and if the next input is greater than the maximum, then we set the maximum to the next input. So when we're done with that loop, we're going to print the largest value is maximum. And I just realized I don't have an F string here. Now I'm going to show you a trick about converting things to F strings. So let's hope this works. But we should be able to do this. First, move the end of the string to there. Okay. And then we're going to get rid of that quote. So now this is the normal string, right? Does that look good? And maybe we should put a period there. Okay, that looks good. Now, if you have a normal string, I don't know when they added this into PyCharm, but it's cool. If you have a normal string and you just put something into curly braces to say, oh, this is a variable name, it should change it to an F string for us. And it did not do it. Well, that was it usually works. I don't know why that didn't work, but it did. Okay, now we're going to turn it to F. All right. That works sometimes. Apparently it's still a little buggy, or I haven't understood the nuances of perhaps it all had to be in the string to begin with. I don't know. Okay, so now let's run this. Okay, how many numbers are there? Well, let's say there are 5. And enter a number, 11, 22, 33, 44, 55. And it says the largest value is 55.0 because they considered them floats. Okay, so this is a design pattern that will work for finding the superlative of any sequence of things. Okay, again, the largest, the smallest, the longest, the shortest, the prettiest, the ugliest, the smelliest, the most embarrassing, whatever it is, if you're able to measure it with a comparison, you're able to find what you're looking for. Okay, and you just assume that the first one is the one you're looking for, and then as you go through the rest, if you find one that's more superlative, bigger in this case, well, then you replace the biggest with the next one that you found. And when you've compared them all, you're done. Okay? It's a general design pattern that's going to serve you well. Okay. So some design of algorithm lessons here. There's usually more than one way to solve a problem. Don't rush the code the first idea that pops out of your head or pops into your head. The thing about design, think about design, sorry about that, and ask if there's a better way to approach the problem. So in this case, the sequential approach, the design pattern we just saw was the better way. Your first task is to find a correct algorithm. After that, strive for clarity, simplicity, efficiency, scalability, and elegance. And then those are all good things. One is to be the computer. Okay, one of the best ways to formulate an algorithm is to ask yourself, how would you solve the problem? And again, how would you solve the problem if you had the sensibilities of the computer? Okay, it hasn't got that visual intelligence that you have. So what if you took that away from yourself? Well, then how would you solve the problem? The straightforward approach is often simple, clear, and efficient enough. And generality is good. So the consideration of a more general problem can lead to a better solution for some special case. So here we started out with only having 3 things to compare, but our solution really solved a more general problem. Okay, it would identify the maximum no matter how many things that we had to compare. If the max of n I'm sorry, if the max of n program is just as easy to write as a max of 3, write the more general program because it's more likely to be useful in other situations. And this is a tension, right? Um, there's always this idea, do I solve just the problem at hand, or do I design some code that'll solve the more general problem? And the question is, what's the incremental cost? If there's just a small incremental cost, well, and I would say that that's what we had here. Well, then solve the general problem. If it's a substantial incremental cost and the likelihood that you're going to use it for other problems isn't high, well, then solve the problem at hand. Don't reinvent the wheel. If the problem you're trying to solve is one that lots of other people have encountered, find out if there's already a solution for it. Okay, so it turns out, right? It turns out that there is a solution for the maximum. There is a function max, okay? And we could have applied it to a list, okay? But then we wouldn't have had the fun that we just had. So there are times when you want to use built-in things or functions and packages, and there are times when you want to learn yet another technique. So in this case, we've gone with the other technique. As you learn to program, designing programs from scratch is great experience. Truly expert programmers know when to borrow. Okay, and generally speaking, and I repeat this a lot in class or in the lectures, when you're doing this on the job and you're not trying to learn how to write a particular algorithm, you always want to ask yourself, is there an already built version of this kind of code in one of the packages? And then first, how do I find it? Usually with a web search. How do I learn how to use it? Maybe from the documentation, maybe from some kind of a tutorial, right? So in the long run, this idea that we're not going to write code that people have already created and tested and agreed to maintain is a good idea. In the meantime, you're just going to have to take my lead and the lead of the course for which situations do you want to design and write a solution from scratch, and where are we looking for you to maybe go find a function from one of the Python packages. And that is the end of the chapter, and I'm going to say bye until next time. Bye-bye.